So, although for semi-batch reactors, I would like you to pay attention and study on your own time some of the types of reactions for which a semi-batch reactor will be used, it's worthwhile to note that they are often employed in the pharmaceutical industry, in biochemical industry, in industries where we have got highly exothermic reactions, so we want better control of what happens in our reactor, where we have competing reactions, etc., etc. What should be noticed is that they mainly process reactants and products in the liquid phase only. So we are going to restrict our analysis to liquid phase reacting systems. As for any reactor, our starting position is of course the mole balance that we can write for all our components. Under steady state conditions, this change with time is equal to 0 in the number of moles of that specific component, and that of course is true when we model our CSTRs, our PFRs, our PBRs. So in a semi-batch reactor, this term is now not 0 because there's an accumulation just like with a batch reactor inside my vessel. So of course in this case time is our independent variable, and at time is equal to 0 when we have these fed batch reacting systems, I may actually have some of that component already present in my reactor vessel, and it may have an initial reactor volume due to that content. Then I feed some of that specific reactant. I can also supplement that by feeding some of my other reactant. So this is, let's say, if we consider the reacting system that we are analyzing here. So we've got component A, we've got some A already present at time 0, and then we continuously feed some of component B in here. So I've got a FA at my inlet, FA that flows into my vessel, and I've got FB that flows into my vessel, and I've got no outflowing streams in the example that we are going to consider in this case. It is easy to get confused with all the different concentrations that are in play when we do this kind of analysis. So what we need, we have an inlet concentration. So maybe, rather write that as CAN, and we've got a volumetric flow rate N. So of course their product will give me the molar flow rate of component AN. Then I've got a Ca that is present at time is equal to 0 inside my reactor. So that will of course be just the Na0 divided by the volume. So if I write my mole balances in terms of concentration, I will need that as my boundary condition at the start when time is equal to 0. And then of course I'm going to have this changing concentration of A with time. So this is the one for which I am going to set up my differential equation. And for component B, exactly the same thing. I will have my boundary condition when time is equal to 0, and for component B, as I specified it now orally in this example, there is no B initially present, so that's my boundary condition for the integration, my initial value. And then I've got the inlet amount, inlet concentration of B and its volumetric flow rate that will give me this molar flow rate for component B at the inlet. So with these semi-batch systems, the volume in this mole balance is now not a constant, and we need it not only to be multiplied with our volumetric rate, sometimes we can also have the mass-based rate, and then it will of course need the amount of catalyst that's present in our reactor to catalyze that system. But we also need the volume when we want to calculate our concentrations, because we need that in our rate equation. So that of course, the concentration of my components will be equal to the number of moles that's present at any moment in that reactor. So that will be a function of time divided by volume, which will now also be a function of time. So we have an equation that describes our rate as a function of concentrations, and we have an equation for each of our concentrations in terms of the moles, and we can do a mole balance for each of the component divided by that volume. So in terms of unknowns, we still need an extra equation to calculate the volume, the changing volume in our reactor. The starting point for this is our mass balance, the total mass balance. That says the change of mass content inside my reactor with time must be equal to mass in minus mass out. And of course, in this example, I don't remove any mass from my vessel. So in this mass balance, I now want to see how the volume changes with time. So I replace mass with density times volume. And of course, this density is the density of this reacting mixture, which may in fact also change with time because there is some conversion. I change A and B to C. I continuously feed B and C. And of course, this inlet is then, if I write everything in terms of density, the mass flow rate N I can write as the sum of densities of my inlet streams times the volumetric flow rates. And now we are going to make a simplifying assumption. We are going to say the density inside my reactor at any time t is equal to the density of all the inlet streams. So because we have got liquid phases, whether the density is therefore, let's say 800 kilograms per cubic meter if I feed a lighter component, or whether the density is about 1000 kilograms per cubic meter, we are going to make this very important simplifying assumption. So what that implies is that density does in fact not change with time. So in this differential equation, it is a constant that I can take out of that equation. So now in my mass balance, I can then take this out of that differential equation, and I make the further simplifying assumption that all the densities are pretty much, let's just be truth, so pretty much equal. So therefore, they will cancel out. And it seems as if we have done a volume balance, but it's very important to know that we made this simplifying assumption. People will laugh at you if you do a volume balance without stating that this is the simplifying assumption that you made. So therefore, we've got our extra equation for calculating the volume. So I want to now show you two different ways in which we can solve this set of differential equations. So in effect, we've got a differential equation for A. We've got a differential equation for B. We can add the differential equation for C, of course. It's optional because unless you're asked to plot how the concentration of C changes with time, we do not need it because it does not feature in our rate equation. And we've got our how does our volume change with time. The first approach, described on the slide here, wants us to rewrite the differential equation so that concentrations of the different components inside this reactor is the dependent variables and not the number of moles as they change with time. So this requires us to do some calculus, and it's great fun because we can flex our mathematical skills muscles. So in this differential equation, of course, just rewrite that in terms of concentration and the volume, which will also then change with time. Apply the product rule to write that in terms of the two differential equations, and then combine, rearrange to make that the subject of the equation. And of course, remember, this is now the one that we've just derived from the mass balance, but assuming that the densities are not only constant but equal. The only risk with this approach is that you do not keep your ducks in a row and get confused with which concentration to use where. Remember, for Fn, you have to use the concentration at the inlet, which is not the same as the concentration inside that reactor. To initialize your integration, regardless of which numerical integration function you use, you need the initial concentration of component A and component B inside your reactor. So if you don't get confused with the different concentrations and you substitute the correct concentration everywhere in your rates and in your integration boundaries, all will be well. An alternative approach that's easy to implement in Python is to keep the mole balances in terms of the number of moles as the dependent variables, and then just complement them with algebraic equations to calculate the concentrations needed in order to use the algebraic equation for your rate equation in terms of concentration. So I've got my algebraic equation sets complemented by my differential equations in order to satisfy my degrees of freedom. So I'm going to use solve IVP to integrate over time. I've got a specified time horizon which I need to give in a list. and I calculate my inlet molar flow rate so that I can use them in my mole balances. And I also calculate my initial values, which will be true at time 0, that I can use to initiate my integration procedure. So just a note on using solve IVP, other than ODE int, it doesn't give you a smooth array of values because it just integrates between these two boundaries, which is a list, and it decides where it needs to go depending on the slopes of your differential equations. So if you want a smooth output, switch dense output through on as an option in your procedure where you calculate all your results. And then you can specify a span of values, just like you would with ODE int. So I've got a lint space of 0 to the last value of in that list. So it's going to give me 100 intervals. And now I can calculate the y values at each of these time intervals. And all I've done is just to unpack them already in terms of NA, NB, NC, and the volume. So the way you do it is you use the .sol attribute. So you say, take that result that you now get, and .sol, find the solution at all the t-span values that I have specified. And it's only going to calculate the y values, which is all your dependent variables at each of that independent variable positions that you asked for it. So now if I want to plot concentrations, of course, I have to do some algebra afterwards because I haven't got concentration as my dependent variables. So just plot it as NA divided by volume, NB volume, NC divided by the volume.